Apologize, guys. I just realized I forgot to start my recording, so we're going to be missing part of this presentation. We'll get the last part, and we'll get some examples that I have planned. So if you're looking, if you need to review this lesson, I would probably recommend looking at another class period's recording after today. So sorry about that. I made a mistake. That sucks. Sorry. All right, moving on. If I can. What? Oh man, I'm just clicking all the wrong buttons today. All right, so the next thing we need to be able to do sometimes is choose a sample size. All right. So in planning a study, we may want to choose a sample size that allows us to estimate a population proportion within a given margin of error. The margin of error, ME, in the confidence interval for P is, right? It's what's on the right-hand side of the plus or minus in our interval when we calculate the interval, right? So ME equals Z asterisk times square root of P hat times 1 minus P hat divided by N. And again, Z asterisk is the standard normal critical value for the level of confidence we want. Right, so that's determined based on the confident, like 90% confidence interval, 95%, 80%. That's how we help. That's why we find Z asterisk. Right. Because the margin of error involves the sample proportion P hat, we have to guess the latter value when choosing N. There are two ways to do this. So sometimes we might not have P hat to start, right? Because we haven't sampled yet. Right? This is involving choosing the sample size, meaning sample hasn't been taken yet. So we can use a guess for P hat based on a past experience or a pilot study, meaning we have maybe a small sample that was taken previously that gave us a proportion, a sample proportion, and we're going to choose to use that as our guess. Or we can use that P hat equals 0.5 as the guess, because that's going to give us the margin of error that is largest. Right, the margin of error is largest when P hat equals 0.5. All right, so these are the two options that we have here. And again, this is based on we're choosing a sample size, meaning we haven't sampled yet, meaning I can't have calculated P hat. So I have to use an estimate so that I can choose the proper sample size based on the confidence interval I want and the margin of error that I want. So anyone want any clarification on that? Yes, Lizette.
I don't really get what you're saying.
Okay. So sometimes before we do a study, we know how confident we want to be, and we know like what's a reasonable margin of error. So maybe it's like I want to have a 90% confidence level, and I want to be, plus or minus within, 3% of my, or I want my error within like 0.03 of the actual value. Like for a proportion, that would be like within 3% of the actual proportion. With means, it plays out slightly differently because we're not dealing with proportions, but we'll get to that next week. So let's say, for example, like maybe I want to estimate the proportion of AP Stats students who, let's use our height example, who are like taller than 5'6", right? And previously, right, I collected data from you guys, so I have data to go off of, but maybe I'm considering AP Stats students for the entire district, right? And so I can use that previous sample as an estimate for P hat, say, well, based on the study that I did previously, the data that I have, I'm going to use this as my estimate. And then I can use that for the value of P hat for my margin of error. And that again is based on how confident I want my confidence level. So if I want like a 90% confidence level, we'll use the Z asterisk score from that we previously found with 1.645, and we can calculate a margin of error of 0.03. We'll see an example of how this works out. I have an example planned, and I think there might be one in the slides here too. So this is based on the scenario that we haven't conducted our survey or our sample yet. And I say, well, how many people should I sample so that I get these kind of parameters met, so that I have a confidence level that I want and a margin of error that I feel is acceptable for my estimate. I know it seems super vague right now because it's kind of like, why not just take the sample and figure out if it's good or not? But these are the things sometimes you want to sample like enough, right? Instead of saying, hey, well, we'll just sample 2,000 people. Maybe you could pull off the same thing with 1,000 people and save money, right? As far as like a polling agency is concerned. So that's why this type of calculation would want to be used. It gives us an idea of a starting point so that we don't have to oversample, or that so we don't undersample. Does that help at all, or did that just make it more jumbled?
Yeah, that did help. I understand a bit better. Thank you.
Cool. You're welcome. So here's something for our notes here. In planning a study, we may want to choose a sample size that allows us to estimate a population proportion within a given margin of error. Right, so we have calculating a confidence interval to determine the sample size, N, that will yield a level C confidence interval for a population proportion P with a maximum margin of error, ME. Right? Solve the following inequality for N. And we'll see an example of this, where P hat is a guessed value for the sample proportion. Right? So we can use what we saw on the previous page. We can guess based on a previous sample, or we can use 0.05. Right? The margin of error will always be less than or equal to ME if you take the guess P hat to be 0.5. Right? So that's why the 0.5 as a guess is kind of like, well, if I don't know what else to use, just use 0.5, because we're guaranteed to have a margin of error less than or equal to what we want if we use that value. So you need a moment to write this down. So here's an example. So a company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service measured on a 5-point scale. The president wants to estimate the proportion P of customers who are satisfied, that is, who chose either satisfied or very satisfied, the two highest levels on the 5-point scale. She decides that she wants the estimate to be within 3%, 0.03, at a 95% confidence level. How large a sample is needed? So here we have our bunch of context here. So here's our problem. We need to determine the sample size needed to estimate P within 0.03 with a 95% confidence. Critical value for 95% confidence is z asterisk equals 1.96. And this is what we found previously, way earlier in the presentation. Right, we used to estimate this as 2. We know we can get a little more accurate using table A to 1.96. We have no idea about the true proportion P of satisfied customers, so we decide to use P hat equaling 0.5 as our guess. Because the company president wants a margin of error no more than 0.03, we need to solve the equation that our margin of error is less than 0.03. So again, this is just, we're kind of identifying the pieces that we need to solve this problem. Right, we have our, what the problem is, our confidence level with our z asterisk, what we're going to use for p hat, what we're going to solve. Because the company president wants a margin of error no more than 0.03, we need to solve the equation 1.96, that's our z asterisk, times square root of p hat times 1 minus p hat over n is less than or equal to 0.03. Right? So we multiply both sides by square root n and divide both sides by 0.03. Right? That leaves us with our variable on the right hand side and a bunch of numbers on the left hand side, which we can calculate. Square both sides, and we're left with 1.96 over 0.03 squared times 0.5 times 1 minus 0.5. 0.5 is less than or equal to n, which ultimately leads us to 1067.111 is less than or equal to n, which we can also read as n is greater than or equal to 1067.111. So we round up to 1068 respondents to ensure that the margin of error is no more than 3%. Right, this is saying that I need to use a sample size larger, at least this or bigger than 1067.111. So rounding up is really the only option. Rounding down, I could get a margin of error that is not what I want. Is there anything I can clarify here on the math or the reasoning? Excuse me. Does anyone need a moment to write anything down? All right. Excuse me. All right, so that reaches the end of the presentation. All right. And so now what we're going to do is actually look at a couple of other examples. These are some problems that I selected from the practice problems for section 8.2 from the textbook that involve all the parts of what we saw today. And this is because some of the comments that I've seen in the free response FRQ sub-assessments is that you guys would like some more examples during class time. So I have some examples ready so we can see some more complicated examples and not just like the ones that they do here in the presentation. So with that, I need to and go here. Yes, okay. So here we go. I need to move this away. This. All right. So we're going to look at two different problems here. So yeah, we're going to get started. Welcome. Excellent. There we go. All right. So our first question, going to the problem. This is actually related to a previous problem that we saw in our 8.1 practice in class last week. Tanya wants to estimate what proportion of her school's seniors plan to attend the prom. She interviews an SRS of 50 of the 750 seniors in her school and finds that 36 plan to go to prom. Identify the population and parameter of interest. That is question A. All right. So, right, the population is the seniors at the high school. Right. The parameter of interest is the proportion of seniors. Cannot write today. Who plan to go to prom. So again, I've answered the question. I wrote complete sentences. This is good. All right. Part B, check the conditions for constructing a confidence interval for the parameter. All right. So that means we must check that it is random, 10% condition has been met, and the large counts condition has been met. Give myself a little more space. All right. So, and here. So random. Yes. And you took an SRS. It's really all we need to say. We know it's random because it was a simple random sample. %, all right. Since 50 is less than 10% of 750, the 10% condition is met. And finally, we have our large counts. Since 36 and 14 both greater than 10, the large counts condition is met. Right. Can anyone tell me where the numbers 36 and 14 came from and why I used them?
The 36 came from the people who are going to prom and 14 who are not out of the 50?
Correct. And thank you. Was it Giovanni? Thank you, Giovanni. So yeah, exactly. 36 people plan to go from our sample and 14 said they were not going to go from our sample of 50, right? The large count condition says the number of successes and the number of failures both need to be greater than or equal to 10. That condition has been met, so we're good. We could also write this out as the calculation and say n times p, n p hat, or yeah, n times p hat was greater than or equal to 10, n times 1 minus p hat is greater than or equal to 10, but in this case we have the actual values, so yeah, it's easier to just write them out. So, excellent. B has been answered. Yes, Matthew.
Wait, I get confused. Where'd you get the 14 again, Mr. Mosley?
50 minus 36. It's the remaining proportion of students from our survey who said that they weren't going to prom because they weren't part of the 36 who said they would go. Yes, thank you for asking for clarification. All right, so part C now is where we construct a 90% confidence interval for P. We need to show our method and then interpret the interval in context. All right. Give us a little more space. Okay. So we know, or at least right now we have P hat. Right, that is our 36 out of 50. And that is our 0.72. Right. We want a 90% confidence interval. Right, this leaves 10% split between the two tails. Right, our conditions have already been met, so we know that we're using a normal approximation here. And yeah, using the one method that we have so far. And so this 10%, right, means that we have, oh wait, not 0.05, 0.005. Wait, am I not mathing well today? I'm not mathing well today, sorry guys. 0.05 is right. All right, so we have 0.05, right? This is the value that we need to find in table A on the interior. And we saw them find this earlier in the presentation, and we know that this results in a z-score of negative 1.645, which that means that we have a z asterisk of 1.645. Okay. I'm gonna add a thing in here. So one thing I want to add to this here, the method we're using, right, is the one sample z interval. For a population proportion. All right, so again, we have our z asterisk. We need to find working towards our interval here. So we find that standard error, which will be equal to z asterisk times the square root of 0.72. Yes, Chow, did you have a question? Chow, do you have a question? Okay. All right. We have 0.72. Okay, no worries. Times 0.28 over 50. We have 1.645 times this 0.72, 0.28 over 50. All right. Yeah. And I need my calculator. So this will get us 1.645 times 0.0635. That gives us a 0.104. Yeah. So this becomes the number we plus or minus 2 p hat. So the interval that we get here, we have 0.72 plus or minus 0.104. This gives us our interval, so we get on the minus side 0.616. And on the positive side 0.824. Right, so we get this interval all right, 0.616 to 0.824. So finally, right, this is our this is the confidence interval. That we were looking for. And now we interpret the interval in context. So again, this gives us that kind of sentence frame that we've been using for intervals. And we are 90% confident that the interval from 0.616 to 0.824 contains the true proportion of seniors who plan to go Right, so again, I'm not just saying that it contains the true population proportion. I am talking about the context from the problem, which is dealing with the proportion of seniors who want to go to prom. We want to be specific. Okay. Is there anything I can clarify for you? Any questions? And sorry, my writing's all over the place. There's no lines. Good. Are we okay to move on to the next example? Okay. Take that as a yes. All right. Example number 2. The national opinion poll found that 44% of all American adults agree that parents should be given vouchers that are good for education at any public or private school of their choice. The result was based on a small sample. Right, so this is based on a previous small sample. So how large an SRS is required to obtain a margin of error of 0.03, that is plus or minus 0.03, in a 99% confidence interval? Right, answer this question using the previous poll's result as the guessed value for p hat. Right, so it's kind of nice. The question is telling us what to use for p hat, right? Our 0.44. So that's kind of nice. So we'll start with that. So we have our p hat is equal to 0.44. All right. We want to find the z asterisk for a 99% confidence interval. All right. So to do that, we have to figure out like what's left on the two tails, right? So if we're looking for 99%, that leaves 1% to split between both tails, right? So this means that we have 1% split. That gives us 0.005 for each tail. So we find 0.005 on table A. So bring up my table A. That's a previous example that I don't need there anymore. Why is it there? Sorry, I don't want to add confusion here. All right. So we need 0.005. So we're looking through, we have 0.04, 0.04. Go. So again, we have 0.0051, 0.0049. Right, these are the two closest to 0.005. Right, which means we're going to use this negative 2.5, and we can split the difference between these two and go 0.075. Right, so then between these, right, that would kind of meet us right here in the middle, which is what we want, 0.05. So we'll use negative 2.575 for the value of z. Right. So that means that z asterisk is 2.575. All right, so excellent. We needed that value. And now we have to set up our equation and solve for n. Right, n is what we're looking for here. We want the proportion or the sample size. All right, so let's go. So I'm solving the equation here. We have z asterisk times p hat 1 minus p hat over n is less than or equal to the margin of error. So we'll replace this with the values that we're using. And we get 2.575 times the square root of 0.44 times 0.56 over n is less than or equal to 0.03. And so we've put in all the values that we have, and we need to solve this for n. Right? So we can rewrite this as 2.575 times the square root of 0.44 times 0.56 divided by square root of n. It's less than or equal to 0.03. Okay. I will now multiply each side by the square root of n and divide each side by 0.03. Right, so we have square root of n, right, divided by 0.03, multiply, and we do the same thing on this side, square root of n divided by 0.03. Right, the 0.03's cancel here, square roots of n cancel here. We get 2.575 times the square root 0.44, 0.56 divided by 0.03 is less than or equal to square root of n. We then take the square root of each side, or the square each side. And we get less than or equal to n, and n is greater than or equal to 1,815.32. Approximately. All right. So now we have the value of n, and again, we'll round this up to 1,816. All right. So we have that an SRS of 1,816 would be required. To obtain a margin of error of 0.03 in a 99% confidence interval. Right. So, any questions? Anything I can clarify on what all this crazy math just did? So now question B is saying answer the question in part A again, but this time use the conservative guess p hat equals 0.5. By how much do the two samples differ? Wow, I have a typo. Oops. All right, so I'm going to take a shortcut on this because I've done a lot of the legwork already. And if you notice, this here essentially gives me, right, this part here gives me a formula I can use to get n without doing all the rearranging, right? If I want, I can say, well, n is greater than or equal to z asterisk, the square root of p hat 1 minus p hat over margin of error, all of that squared. That's all the parts that we have over here on the other side of our inequality. So I can kind of just take that and do this calculation a lot faster. I already know z asterisk. I just need to replace the values of p hat. And I already know the margin of error. Right. So we can say that n is greater than or equal to 1 point, oh, sorry, that's from the previous example. 2.575. Give myself more space here. Times the square root of 0.5 times 0.5 over 0.03. That whole thing squared. All right, and we get n is greater than or equal to 1,841.84. So we would need an SRS of 1,841. We'll round that up. And this differs by 26 samples. From the result in part A. All right. So once you understand the formulas, there are ways to kind of do these things faster. But it's important, like if you're using like this shortcut formula, you need to be really explicit on where these values are coming from. So it's clear to, like on the AP exam, the grader, what you're doing. So any questions? Anything I can clarify? All right. I have not typed up the practice problems yet. I'm going to do that today. So they will become available later today. As far as other practice problems, and hopefully I'll be able to get the solutions done today as well for section 8.2. Right. So, other than that, I know that the lesson went longer today than our normal time usually goes, but I wanted to make sure and give you guys those extra examples showing how to use this new concept. If you do have any other questions that come up, or if you need help on anything else, please let me know. Other than that, we will see you all tomorrow for more practice with section 8.2. We'll have an activity to do that will hopefully help you make even more sense out of this stuff. Right, so other than that, if you have any other questions, let me know, and I will see you tomorrow.